Hello, everyone. I'm so sorry. I've been trying to get on for the last 10 minutes. All right, looks like everybody's in here. Again, I'm sorry, everybody. I don't know what was going on. I was having problems even accessing the learn.vccs website. So I'm here now. Anybody have any questions for me? Go ahead and chat me your first and last name like Airly did, and that way we'll go ahead and have you for roll. But do ask me questions if you have any regarding chapters 1 through 4. Our tests, like I said, I'll probably be opening up Thursday, give you till Monday, or excuse me, give you till like midnight Sunday to get it done. So, and I'll be putting up a practice test probably sometime today. I thought I'd get it done last week, but I didn't. So does anyone have any questions on material or anything else for that matter?
Did you ever change the due date of homework number 4?
I went on last night to try to do it, and I had internet problems. I couldn't do it, but I will change it. Actually, I'll do it right now while you're in here, so because it'll be pretty easy to do while I'm letting the rest of the people log in. No problem. Yeah, I was going to change that, and actually, I meant to do it Friday. Then I got sidetracked, and then I said, okay, well, I'll do it on Sunday, and then I couldn't get on the internet last night. I was like, dang it. Yep, I'm doing it as we speak. I am multitasking. Anyone have any other questions, course related, topic related, material related, whatever? No second, no. All right, so you got to be able to do these Newton second law problems. Our next test is actually mostly on 3 and 4, but of course all our tests are comprehensive. The good news is this chapter 5 that we're doing now is actually just a continuance of chapter 4. It's us continuing to use Newton's second law, but in even more robust ways. So doing what we have to do this week is going to help us quite a bit. I'm going to go ahead and push this homework for chapter 4. I'll push it up till Sunday of next week. And I'm not seeing my 4 concepts. Did I never make a 4 concepts?
Real quick, I remember you said something about something happening on Wednesday. I forgot what that was.
Oh, okay. Yeah, you guys meet on Wednesday. I forgot that. Yeah, I'll be making the actual test available then for you guys to get done. So basically, it'll either come up on Wednesday or Thursday, and you will have until Sunday night at midnight to get that done. I don't know why I didn't make the chapter 4 conceptual available, but I'll make that available, and you'll have until Sunday to get that done as well. Any questions on any other stuff? All right, well, I got that part set, so we're good to go on that. I want to show you some more things that we're going to learn regarding Newton's second law. Specifically, we're going to discuss friction, and we're going to discuss centripetal acceleration. So there's a certain necessary acceleration that must be carried out in order for an object to go in a circle. So we're going to work on that, and I'm going to do a slightly different derivation than a lot of classes and a lot of textbooks do. But let's first off start with friction. So it turns out, let me go ahead and give you my document cam. So it turns out that the friction force on an object is directly related to the normal force. So remember we taught you about the normal force last week, and one of the main things I wanted you to see from that is the normal force is not always the object's weight. It's not even always equal in magnitude to the object's weight, and it is in fact in the opposite direction often of the object's weight. So what we do is we say that there's actually two types of friction. And we use a script F for this. There's a static friction, which is less than or equal to the coefficient of static friction times the normal force. And what I mean by this less than or equal to, obviously friction, which you guys sort of recognize as a force that keeps things from moving, in some sense is also the only force that allows us to make things move. So it's a little bit of a misnomer to say it that way, or at least a misdefinition to say it that way. But what it really is friction is a force that keeps one surface that's touching another from moving with respect to one another. So that's the friction force. And what we're saying by this equation is the friction force is never going to be so big that it just takes this pin and pushes it to the right out of the blue, right? So it's only going to provide as much friction force as necessary. Right now, there's no friction force necessary because there's no forces being applied to it. If I apply a little force to it, then it's got to try to, as long as it's not moving, it's going to try to resist that up to some maximum amount of force. So I can push it real lightly and it doesn't move. That means at that point, the friction force was less than mu static, which is something you can derive experimentally, times the normal force. And if I push a little harder, I still would lose. In other words, I still wouldn't get it to move. That means I'm still below that. But eventually I'm going to get to a point where I actually overcome that force and then it actually moves. You guys might try it with your calculator, especially if your calculator is the type with the rubber tips like this. You can take and give it a push and you see nothing happens, right? And you push a little harder and then finally it starts to slide. But then what you notice is as it starts to slide, it actually is a lot easier to push. In other words, it's harder to get it started than it was to actually keep it moving. And that's the difference between static friction and kinetic friction. And I don't know why I wrote this static. This should have been kinetic. I'm sorry, guys. No, that's static. That's right. I had it right. Sorry. That's the difference between static friction and kinetic friction. Kinetic friction is just equal to mu kinetic times the normal force. And generally speaking, mu static is greater than mu kinetic. And that's what I meant by taking your calculator, put it on your desk or your table or something like that, especially like one with the little rubber stoppers on the bottom so it's got a little grip. And you push a little bit and the calculator doesn't move. You push a little harder, the calculator still doesn't move. You push a little harder and then finally it moves. I think you'll be able to feel that in fact it moves a lot easier than it is to get started. And that's because this mu static is greater than mu kinetic. But again, I wanted to stress the reason I use a less than or equal to is the static force is only going to give it as much force as it needs to keep it from moving, the two surfaces moving relative to one another up to some maximum. Once you reach that maximum, it can't do anything else, and it's just going to switch over to kinetic friction at that point because you've now exceeded the static friction force. Now your force is just constantly going to fighting the kinetic friction, which will be, like I said, less than the static friction. So let's look at a specific example of the type of problem that we could do. So one might be, let's say you have a wall that has a certain coefficient of friction between the drywall surface and the actual box that you're holding. So this is a box, and let's say its mass is 10 kilograms. Okay, and in fact, let's say you're pushing on the box with a certain amount of force. Okay, what we want to find is what is the force necessary to keep this box from falling. Okay, because notice you're only pushing horizontally. So this force F is the question mark. What's going on here is this mass has a weight, m times g, wanting to pull down on it. It has a normal force pushing back on it, and that normal force, of course, is related to this force. But that normal force also gives us a static friction. So we want to provide just enough force to allow static friction to hold this box up. Okay, so I draw a free body diagram. The free body diagram suggests that this force right here is 980 newtons. We have a normal force acting this way. We have F acting this way. And then we have a friction force, of course, acting this way. And that should be a static friction force, which best case scenario, the maximum it can be is mu static times normal force. So I'm wanting to find out the minimum force, which is meaning this one's going to be the maximum. So I can actually call it mu static times the normal force. Okay. And this is the F question mark. Okay. Let's say the coefficient of static friction mu sub S is 0.13. Okay, like I said, this is something that you experimentally can determine. One of the experiments we usually do in an elementary lab is you put a box on an incline and you slowly up the incline and just give the incline just a slight tap. And the angle at which that slight tap causes the box to slide down, if you take the inverse tangent of that angle, you end up getting the coefficient of static friction. So that's a typical way of determining this. So let's look at this. According to Newton's second law, the summation of forces is equal to mass times acceleration. In this case, we actually want no acceleration whatsoever. So first off, we got to do the summation of forces in the x direction equals mass times acceleration in the x direction, but the acceleration in the x direction, of course, is 0. So I'm going to call this the coordinate system. To the right is positive x, up is positive y. So I'm going to say this friction, this F force that we're trying to find, the unknown, is actually in the positive direction, and the normal force is in the negative direction. So I'll say F minus F normal is equal to 0, which tells us F normal is actually equal to F. Okay. Now the summation of forces in the y direction equals mass times acceleration in the y direction. Again, we want the acceleration to be equal to 0. So in this case, we're going to have the 980 newtons pointing downward, so that's a negative, and we got the mu static times the normal force. So it'd be mu static times Fn minus 980 newtons has got to equal 0. Okay, so that tells us that the normal force must be equal to 980 newtons divided by mu static, which equals 980 newtons divided by 0.13. Notice the coefficient of static friction has no units. It's a unitless number. It's a dimensionless number. It's also called a non-denominate number. I'll say 980 divided by 0.13, and that gives me 0.007. Oh, that can't be right. Oh, excuse me. Yeah, it's 7,500. Okay, so it'd be 7.5. I'll go with an extra sig fig, so I'm gonna call it 7,540. So 7.54 times 10 to the third newtons is what the normal force has to be. But we already found that the normal force is equal to the force. So in fact, the force that we want to know has to be at least 7.54 times 10 to the third newtons. So does everybody get what we did there? Any questions on that?
Can you zoom up on it a little bit? I can't.
What is the M thing? I think that's a Greek letter, but what does it symbolize?
It's the in this case, it's the static coefficient of friction. In this case, it's the kinetic coefficient of friction. I don't know why I wrote in there, but it's K for kinetic.
Okay.
So it's the basically what you have to multiply by the normal force to get the friction force that you can achieve. Okay, and like I
Oh,
said, experimentally, we would determine that by putting a block on an inclined plane whose angle you can change, and then slowly move the angle up, give the inclined plane a slight little tap, and if you do that and the box stays still, then you know the coefficient of friction is going to be bigger yet than the tangent of the angle. You keep doing that over and over again until you finally get the spot where giving a little tap causes it to slide down the incline, and you take the tangent of that angle and it turns out to be the coefficient of friction. So
okay.
that's an experimental way of determining it.
So
Now,
in problems, would that be something that we're like given, or would we have to?
yeah, and if you look at your textbook, they'll normally give you, every textbook normally gives you a table with coefficients of friction, both static and kinetic. And it basically depends on what the two materials are made of. So like you can imagine if this was made out of, let's say, cardboard, and then this wall was made out of really smooth teak wood, you'd probably find a very little coefficient of friction. Whereas if you made this box out of rubber and had this teak wood, the coefficient of friction would be a lot larger.
Okay.
So
Thanks.
basically depends on the two surfaces in contact.
Yeah.
Okay. So another problem that's classically done is the one that I just mentioned to you, which is what is the coefficient of friction on an inclined plane if the angle is such that it just barely accelerates. So let's call this angle theta. Okay. This is an inclined plane. The angle theta is the angle of the incline. I'm going to put a box on it like so. Okay. And I'm going to give that box a mass m. And what I'm going to try to do is calculate at what angle the friction force is exactly the same size as the force that's pulling it down, because that's when it's in equilibrium. Okay. So I'm going to tilt my coordinate axes again. And this time I'm going to call this the positive x direction, and I'll call this the positive y direction. Okay. That's supposed to be parallel to the inclined plane. Never mind that horrible drawing. All right. So my free body diagram for this is basically, I'm going to treat it like it's a dot, and I'm going to have a weight mg here. And as we know, this line is vertical, this line is horizontal, so this is a 90-degree angle, which means this angle is 90 minus theta right here. And now I'm going to convert this mg to components of a triangle that are parallel and to the individual axes. So this one's going to be in the negative direction. So I'll draw it red. And this one's going to be in the positive direction. So I'll color it green. And now once I realize that this is perpendicular to this surface, then I see this whole angle right here is 90 degrees. And since it's 90 degrees, then this one is 90 minus parentheses 90 minus theta. When you do 90 minus parentheses 90 minus theta, you just get theta again. So this angle must also be theta. Okay. Now the other force that's acting, or the other forces that are acting on this, are going to be the normal force in the y direction. And remember, the normal force is always perpendicular to the surface, not necessarily, anti-parallel to the weight. It's actually perpendicular to the surface. And then there's another force, in fact, that's going to be acting in the negative x direction, which will be the friction force. Okay. Now the maximum that can be, and therefore that's the one we're considering, is mu s times the normal force. Okay. So I would like to find out what is this angle theta at which this mu static times Fn is just enough to counteract the force pushing it down. Okay. So using our trigonometry, we can say that, see that the cosine of theta would be adjacent, which is this side, over hypotenuse, which is mg. So it's going to be, this side right here will be mg cosine theta. And sine theta would be opposite, which is this guy, So opposite over hypotenuse would be this side over mg. So this side must be equal to mg sine theta. Does that make sense to everyone? Everybody sees that, hopefully? So we're assuming the block is not bouncing up and down. So in this fancy y direction that I've created, the summation of forces in the y direction is equal to mass times acceleration in the y direction. But since that block isn't bouncing up and down, we know that acceleration is 0. So that gives us F normal minus mg cosine theta is equal to 0. I'll call that equation 1. The summation of forces in the x direction equals mass times acceleration in the x direction. Again, we're trying to find the point at which the mg sine theta, what angle theta at which this is just equal to that, because I know if I push it up just a little bit larger, then that thing will actually slide down the incline. Okay? So in this case, I'm actually examining again an acceleration equal to 0, but the forces I have are mg sine theta minus mu s times Fn, and that's got to equal 0. And this is equation 2. So let's write equation 2 a little differently. I'll call this 2 prime because it's 2 that's been manipulated. I'm going to say that this is mu s times F normal is equal to mg sine theta. And I'm going to rewrite 1 as well and call that 1 prime. I'm going to say this is Fn equal to mg cosine theta. So I have a system of equations, 2 equations, 1, 2, and 2 unknowns, normal force and theta. I didn't ask you anything about the normal force, but I did ask you about the theta. Can anybody think of a way to solve this system of equations?
Could you like divide each equation by each other and then it would turn into tangent theta and the mg's would cancel out?
Exactly, as would the FNs. Exactly, that's exactly the hint that I wanted to y'all to pick up from last time. So yeah, if I divide 2 by 1, then obviously the normal forces are going to cancel out, and I get mu static is equal to the mg's cancel out. So there's my FNs canceling out. Here's my mg's canceling out, and sine theta over cosine theta is tangent theta. So that's what I hinted to earlier, that the coefficient of static friction can just be found by doing this experiment and finding at what angle theta this block would just start to slide down. And you just make sure this block is made of one of the materials that you want to know, and the incline's made of the other material. So theta, which is what we really asked for, is equal to the inverse tangent of the static coefficient of friction. Ain't that cool? So that's a fairly neat, typical problem that you have to be able to do. It gets more complicated, as you'll see in a second. I'm going to show you a couple other examples. But does anybody have any questions on this one? Someone said the letters are blurring because of low resolution, which I assume is my Wi-Fi band or my bandwidth. So I'm going to run over this again just to make sure everybody can see it. There's the force. And then this one was this. We were asked for theta. Theta turned out to be the inverse tangent of the static coefficient of friction. Hopefully that was good enough. Like I said, all these will be in the Google Docs as well. I heard somebody say something. Did someone have a question? All right. So let me show you a neat little trick real quick. I want to go ahead and do another inclined plane problem, but I wanted to show you this neat little derivation before we do that. So I'm going to try to make a R vector. And remember, I mentioned to you that we use a R vector just to suggest a point in space. So if you wanted to, say, track the position of a projectile over time, you would make a R vector that points from the origin of your coordinate system to that projectile at any point in time later. So I'm going to do that, but I'm going to do it for a very specific type of motion. I'm going to do it for a motion in which an object is going in a circle about the origin. Okay, so I want this object to be right here at t equals 0. I want x to equal r, and I want y to equal 0. And then up here, sometime later, I'm going to have x equals 0 and y equal r. Okay. Well, it turns out you can do that pretty well. And in fact, if you want this thing to make, notice the radius is actually r. If you make this object want to complete a whole circle, let's say every 1 second, then you've got to make it go the right velocity, right? And that's a horrible circle, but this was supposed to be the center of it. Okay, so I can make this r vector. I can, let's say the x component, if I actually did it like this and said this was r at some point in time t, then I'd see that this angle theta right here can be used to find the x component. X would just be r times the cosine of theta. And I'm going to, instead of saying theta, I'm going to leave it blank for a second. And then the y component would just be r sine theta. And actually, I should leave that not as theta either. And I'm going to put a j hat on that one. So there's my r vector. And I think you can tell that as theta progresses, once theta, for instance, gets to pi over 2, then you'll see that the cosine of pi over 2 is in fact 0, but the sine of pi over 2 is in fact 1, so I get exactly the point that I want, and so on and so forth. Now, the distance around, the circumference, in other words, is 2 pi times r, and let's say we want the object to complete one circle in a time t. So that time t is called the period, and I'll use the Greek symbol tau for that. Okay. So that would mean the velocity of this thing would have to be 2 pi r over tau. And therefore, if I just multiplied this velocity times time, I would end up getting basically the distance that's traveled at any point in time t. Does that make sense to everybody? The distance that's traveled around this way. So I could actually make this, incorporate this in here somehow. So this 2 pi r gives me a distance per time. And then if I multiply by time, that just gives me a distance. But in fact, I don't want a distance. I want an actual angle, right? Because I'm taking the cosine of something. So if I took that time and divided it by r, then I could get just a pure unit of radians, for instance. So let's say r is equal to r cosine. And what I'm going to do is just call this omega t, I hat, plus r sine omega t, j hat. So omega is going to be equal to 2 pi over the period. And t is just going to be the time. So in other words, by getting rid of this r here, I could talk about something that's more like a angular speed. In other words, I divided the linear speed, 2 pi r over t, by the radius and got the angular speed, because this is the number of radians it'll complete per period. So notice it's exactly what you expect. You expect the period t, which is the time required for it to go from here all the way to here. That's what's down here at the bottom. So that's the amount of time. And the radians, of course, from here all the way to here is 2 pi. So it's literally the distance divided by the time, but distance being measured in radians. So there's the derivation. That's the actual, that's the deriving of a equation for a vector that gives us a point on a circle at any point in time t. Okay, so it's just r cosine omega t I hat plus r sine omega t j hat. So what would the velocity look like? Well, v is equal to dr dt, which this is a really easy integral. Remember, the I hats and j hats are really constant vectors, so I don't actually have to actually take any derivatives of those. Those are just constants, and the r is a constant. So the derivative of cosine turns out to be negative sine. So I get negative r omega sine omega t. Remember, I had to use a chain rule because once I take the derivative of cosine with respect to omega t, then I got to take the derivative of omega t with respect to t, because that's really the derivative I'm taking. And then the derivative of sine is just cosine, so I'll get plus r, left my hat, plus r cosine omega t j hat. And I thought I wrote my omega in there, but I didn't. Okay, so there's my omega as well in this one. Now the acceleration, and this is the part I'm actually trying to derive for you guys. The acceleration that this object has is going to be, again, derivative of sine, and this time becomes cosine, and then I have to multiply it by omega, so I'm going to get negative r omega squared sine omega, or excuse me, cosine omega t I hat minus r omega squared sine omega t j hat. I think you can tell that the magnitude of this vector is actually r times omega squared. Everybody sees that the magnitude of that vector would be r times omega squared? Because if I have to square all this, and that'd be r squared omega to the 4th cosine squared, and I'd square all this, and that'd be r squared omega to the 4th sine squared. If I factored out the r squared omega to the 4th, I'd get cosine squared plus sine squared, which is just 1. So that would just disappear, and I'd have the square root of r squared omega to the 4th, which is r omega squared. Everybody get that?
Wait, so the cosine and sine there are squared?
When you actually take the magnitude, let me go ahead and compute it for you. Okay. So the magnitude of the vector is the square root of negative r squared omega squared, and of course squaring the negative is going to make that positive anyways. Cosine squared omega t plus r squared, oh, this should have been the 4th, by the way, omega to the 4th sine squared omega t. Right? Now when I take factor out the r squared omega to the 4th, I get cosine squared omega t plus sine squared omega t, which you guys know is just 1. So the square root of r squared omega to the 4th is just r omega squared.
Okay, that makes sense now.
Okay. Yeah, ask me to show you anytime. I usually try to get y'all to guess it ahead of time, but like I said, if you can't see it immediately, it's best to at least see it once. So there's the actual acceleration required to keep this thing in a circle. So in other words, if you don't have this much acceleration, then you're kind of toast. Not only that, notice the direction of this. The direction of this vector, remember you're multiplying by r and omega squared. So I could actually say this vector A is equal to r omega squared times negative. and then it would look just like the original. Actually, I'll pull this over here. Times r cosine omega t I hat plus r sine omega t times j hat. Do y'all agree that this is the same as what I found for that vector? Y'all see that I just factored out the negative omega squared? And this isn't here anymore. So everybody see that I've just multiplied negative omega squared times this to get that? Can everybody see that?
Yeah.
Okay. Do y'all remember what the original r vector was? Y'all see that?
Oh, yeah, I see that.
And what happens when you multiply a vector by a negative number?
It reverses the magnitude.
Exactly. If the vector, like r was here, was pointing that way, then multiplying it by -1 would make it point this way. So what we found out is the acceleration has a magnitude of r omega squared, and it points to the center of the circle. Hence, we call it centripetal acceleration. A centripetal is equal to r omega squared. Now, that's not the way we normally do it, because we normally know things like your velocity. Like if you're going into a turn on an exit ramp on the interstate, you don't know how many radians you're rotating per second, but you do know what your speedometer says, right? Well, what I showed you earlier was that v was equal to 2 pi r over the period, and I ended up substituting for that omega times r. Remember, I took this 2 pi over tau, and I called that omega. So I think you can see that v is just r times omega. So I could say that omega is just v over r. Y'all agree with that? So if I plug all this in, I get r times v over r, quantity squared, and finally I get the acceleration for maintaining a circle. The centripetal acceleration is v squared over r. That is the acceleration necessary to maintain a circular orbit, if you will. Okay, this is what Newton had discovered, in fact, by creating the calculus, and he used that to calculate the acceleration due to the moon. And basically what he did when he calculated the acceleration that the moon had, he basically did this formula. Uh-oh, hold on a second. He basically did this formula, and he took velocity to be 2 pi times the distance to the moon. Well, the distance to the moon is basically 60 Earth radii. So you multiply 60 times the Earth radius, and then you take that and multiply it by 2 pi. And then he knew that the moon takes 1 month, so you divide that by 20. It's actually like 29.5 days or whatever. And when he got that number, when he did that, he got 0.00273. So if you literally take 2 pi times the distance to the moon, that's from the center of the Earth to the center of the moon, which also happens to be 60 Earth radii, and divide it by what we call a month, and that's, like I said, about 29.5 days, and compute it all in meters per second, you end up getting meters per second of 0.00273. Okay? Well, here's the cool part. He said, I wonder if this new force that I'm discovering called gravity, the one that pulls apples to the ground when they're ripe and too full of water, I wonder if that's the same force that pulls the moon out of its straight path and forces it to go on a circular path. Well, this is the acceleration that moon must experience. So if it's if it is the same force, then I expect that force to be weaker, because we're in fact 60 times further away from the moon than we are from this apple, right? In other words, the apple's 1 Earth radius away from the center of the Earth, whereas the moon is 60 Earth radii away. So he took 9.8 meters per second and divided that by 60 squared, because if you double the distance, you decrease the force by a factor of 4. If you triple it, you decrease it by a factor of 9. If you quadruple it, you decrease it by a factor of 16. Y'all see that I'm just going by squares, right? And lo and behold, he got 0.00273 meters per second. And in that instant, he's the only person on planet Earth, the only living creature that we know of that knows the reason for the moon and the planets to orbit the sun is gravity. Ain't that cool? So that's a big deal. We now know what acceleration is necessary, and this is why, for instance, you need to obey the speed limit when you go around the exit ramp. If you get on an exit ramp and it says 25 miles per hour, what they did is basically travel engineers, which are engineers, civil engineers of some sort, they actually calculate the bank of the curve in such a way that you could make that curve with ice being on the surface. So in other words, they bank the curve at just the right angle where you don't need any friction whatsoever. So if you go that 25 miles per hour, you'll go around that curve easy peasy. If you exceed that velocity, though, your tires might not have enough friction to create that acceleration, in which case you end up skidding out and bad things happen. Okay, so that's the centripetal acceleration. I managed to work 2 problems with you on Newton's second law. One involved an inclined plane, one involved a box pinned up against the wall, and then I derived the centripetal acceleration, which we'll use next. Next time I'm going to soup up our Atwood machine, and I'm going to consider a problem like this, say, where you have a block resting on an incline that has an angle theta, say. You have a rope running over a pulley, and then a mass hanging from that side. And you say, you know, what are the various coefficients of friction that you can have such that this block right here doesn't move when these two have different masses? So you can see I'm going to build on that stuff that we did before, which was like Atwood machine was just a pulley with 2 masses, one hanging on one side, one hanging on the other side. Now I've got one on an inclined plane. You can imagine the most extreme case might be a really steep plane and then a non-steep plane with 2 different boxes and 2 different frictions and acting like that. And then, of course, we're also going to attack next time a car banking around a curve, and we're going to be like engineers and design a curve such that that car can make the turn with no friction. Okay, so we now have all the tools to do all that, and in fact, you can go ahead and read your chapter 5 in Giancoli's textbook. You can read that and see how they're actually applying this and the new version for static and kinetic friction to solve these problems. Sorry I was late. It is now time for class to be over. I will wait for the last of you to leave. Make sure everybody went ahead and chatted me your first and last name. And you're free to go. And like I said, I'll wait for the last one to leave, and then I'll go. See you Wednesday, everybody.
Yeah.
Yes.
Did you get, I don't know, I sent it last night, so it's fine if you haven't seen it yet, but did you see the email I sent you?
Who am I talking to?
Emma, sorry.
Gotcha. Yeah, I do see it. Yep.
Okay.
Yeah, I remember seeing it last night, in fact. Chapter 3 homework. Gotcha.
Yeah. Okay, yeah, I just wanted to make sure, because it's not like I'm having trouble understanding it when I read it, but it's just like taking me a while to remember
Gotcha.
what to use for what once I get to the problems. So.
Yes, try to reread your chapter. Now, once I cover the material, here's the best way to study really for this course in general. When you're taking a physics course or a chemistry course, what you ideally want to do is be able to read the material before it's covered, and then have your instructor cover it, and then go back and read it again. And those 2 readings are infinitely different, and both are extremely important. The first one is sort of getting an idea of what's going to happen to you. Then the lecture is what's happening to you. And then the reading afterwards is like you applying what happened to you to understand it. So You might find it better now that you've seen me cover the material. You might find it easier to read the individual examples worked in the book, and then you can more readily do the homeworks from chapter 3. That being said, I did already extend chapter 3 part 2 homework to Sunday night.
Okay, awesome. Thank you. I'll definitely try doing that for the rest of the homeworks.
Yeah, it helps. Like I said, you're gonna, especially the first time you read, when you read the material before I cover it, your eyes are gonna water up and stuff like that. That happens.
Yeah.
What you want to do is try to read as long as you can before that happens, because once you start getting to that point, you're not retaining anything.
Yeah.
Figure out how long that is, and only read for that amount of time. And maybe after 10 times reading like that, maybe bump it by a minute, and
Okay.
slowly stretch out over the semester so you can read it, maybe for a whole. Ideally, you'd like to be able to read for 4 hours straight. That would be a ideal college level reader.
Yeah. Okay, awesome.
Okay.
Thank you.
No problem. See you, Anna.
See ya.
Anybody else? Maria, Orlando, Jacob?
I actually have a question about the lab,
Go for it, Jacob.
Jamie.
Oh, sorry. Another name popped up. Yeah. I looked at the name that was up. Yeah, Jamie, go ahead, bud.
I read that you were regrading labs and stuff, and yet I can't seem to understand exactly what you want us to change with those.
I'm not
rules you gave.
regrading lab 1. What I'm allowing you to do is take what you learned from lab 1, because if you look in your grade for lab 1, you'll see I wrote a lot of comments in there. What I want you to do is take those comments and apply them to lab 2, lab 3, lab 4, which you already turned in, and resubmit them, this time putting the name, naming the file with the word correct in it, so I'll know which one to read. So what you should have is one big, not what you're turning in, but you should have one big Word file. That Word file should be the entire lab write-up that came with your manual, which will be electronic version I give you guys. And when it asks for you to make a data table, you should have a screenshot of the data table put into that Word document. And when it asks for you to do a graph, you should put the graph in that spot on the lab as well. And when it has a data table that you're supposed to fill out, you should type in the actual data into that table in a different color font, like red or blue, than the actual document's already in. And when it asks you to answer a question, you should do the same thing in red or blue. If it's a multiple choice, then just highlight the correct answer with red, make its font red or blue or whatever you choose to do. Just the right one, never do the wrong one. And then save that as a PDF and upload that. That's what the lab format should be.
So basically my crime was doing it in pencil.
The pencil wouldn't be a problem. No, so don't get that wrong. If you're a person that did a lot of the work in pencil, that's perfectly fine. Like if you put your data table in pencil, you just want to take the photograph of your pencil writing. And since that's pencil, I can already tell that's different text. You don't need to change the font color or anything for that.
I scanned it.
Just put it in yeah, that'd be fine. But it's got to be in the right spot, meaning it has to be in the format of the lab manual. And then where the lab manual asks for your data, that's where that data should go.
All right.
Or where it tells you to do that. Does that make sense?
Yes.
It's just when you're grading, 40 some lab reports, it's really hard to pick out the right parts in the right places if they're in different places at every person's lab.
I'm actually quite confused as to why I only got 90 on the first one.
Oh, then you did really well. The 90 is indicative of you mostly doing it correctly. Normally what you missed would be you forgot to do one particular question, that's worth 5 points, or you forgot to do one particular calculation, that's worth 5 points, or you forgot to include a certain graph or a certain piece of data. Each of those I take off in 5-point increments. I can look back at yours and I'll write a more specific comment to let you know what it is.
All right.
I'll probably do that today. Okay.
All right. I'll look forward to it.
All right. See you, Jamie. Tara, Emily, Jamie, anybody? Oh, Jamie's gone. Mimi.
I had just a question about the lab. So, like, I know you post the doc of it, but can we just take a picture of our lab manual and turn it into a PDF?
Take a picture of your lab manual and turn it into what? A
A
PDF?
PDF instead of using your Word document?
Yes, that would be fine, long as you can cut up the PDF, the document that you took a scan of, as long as you can cut it up and put the data tables in the right part of it. That's the
All right,
thing. I
thank
want
you.
the manual. I want it to read just like the manual, except when the manual says do this and get this data, I want the data appear right there.
Okay.
Same thing with the questions and all that. So yeah, any way you can do that's fine, as long as it ends up in one big document and that's turned in as a PDF, then that's ideal. Yeah, Emily, if you just got 5 points off, it was almost certainly not a format issue. Basically everybody got 20 points off or 25 points off for formatting. We still have more time, Emily or Mimi, if you have any more questions.
Yes, for my question, I'm willing to share screen with you because
Okay,
I just don't understand, that's all.
go for it.
For the lab. Are you okay with that?
Yeah, go for it.
Okay. Mm,
Oh no, Mimi disappeared.
did.
Just off the screen. There you are.
So Arturo, one of my lab partners, asked what you mean by answer all questions and turn it in those questions and answer in the format like question 1, answer 1, question 2, answer 2. Have we
Yeah,
got
in other words, as people were turning in like a whole list of questions, and at the bottom will say number 1 answer, and then number 2's answer. I want the question, and then I want the answer to that question immediately below it. I don't. That way, I can easily read exactly the question and the answer at the same time.
the
So that's all it means. Is just make sure the question, the answer for a question follows the question immediately in text.
oh for example, this is my lab too. If I'm willing to show you this, but
Yes.
it is so what I did was in my book I just wrote everything that was
That
correct,
looks perfect. Yep.
and I circled the correct answers like
Those
for
are fine.
you won't take points off for that, right?
No, those are all good. You did those well. The problem is when it has like an actual question, it'll say, what did you get for this? Then that's where that answer should be typed in. Is there any more questions down there? I can't remember how the lab went, but everything you got shown right here would result in no points off. All these look good. Yeah,
Yeah.
all the
So,
answers are right there with the questions, so that's good.
yeah, I circled the right ones, of course.
Yeah, that's good. Yep.
And yeah, for
So like these would have been bad if you put the answers down at the bottom somewhere and didn't include didn't do it right there. That would have been a problem. Like if you took see number question 6 A B C D and E parts there. Sometimes people will go down at the bottom, right? Answer for number 6 is B B F C H E D. That would be bad. But you put them right in line where the question is, so that's exactly what I wanted.
of yeah, so for lab 3 it's the same concept because we're just highlighting the correct answer, so I don't have questions for that. But lab 4,
Mm-hmm.
what I did was I saw in your email that you would take a couple of points off if we have like too many separate Excels, like what I have here. Is that right?
Probably, I think what you're saying might not be exactly correct. I'm not going to take off if you have a bunch of different Excel in there. That's not a problem as long as you've got the ones that I need. So as long as you provide all of the data that you did or made, then you're probably going to be fine. As long as you've got everything labeled. You want
Yeah,
to show me that one? And I don't know what the P and Gs are. Yeah, the problem with this